Namaste. Welcome to this channel, Chemistry Made Easy by Dr.ARM. We were discussing this molecular orbital theory, and in which we have seen the application of this molecular orbital theory to various molecules of the first and second period of the periodic table, that is especially homo-nuclear diatomic molecules. And in case of such study, we have seen the changing order of the molecular orbitals formed as the nuclear charge increases or atomic number increases. So today we are going to consider the correlation diagram for homo-nuclear diatomic molecular orbitals. In this molecular orbital diagram, we are observing the mixing of orbitals of the same symmetry. So when the two atoms from a distance, large distance, interatomic distance, when they are coming closer and closer, when they are reaching at specific internuclear distance, then their atomic orbitals of same symmetry shows interaction with each other, and depending upon the symmetry they will produce the resulting molecular orbitals, and this process will tell us what is the consequence of such mixing of the molecular orbitals when we study the various molecular orbitals of homonuclear diatomic molecules from boron means B2 to F2. So in such case, we observe here, if you see the diagram, you will find that we have shown these atomic orbitals when the two atoms are separated from each other. When the two atoms are separated from each other, means they are at larger distance than interatomic or bond distance. So in such case there is no interaction between these atomic orbitals and there is no formation of molecular orbital. But when these atoms are moving closer and closer, when from a large internuclear distance, when the two atoms are brought closer and closer, means when they reach at the distance here representative shown in dotted lines, vertical lines indicate that the internuclear distance is shown using these vertical dotted lines. So when the two atoms are reaching at this particular range of the internuclear distance, which is shown for B2 to C2, F2, we observe that these atomic orbitals of identical symmetry and identical energy undergo interaction with each other, that is linear combination of their atomic orbitals, and resulting in the formation of new molecular orbitals, in which half of the molecular orbitals are of bonding nature and half of the molecular orbitals are of antibonding nature. So the molecular orbitals of antibonding nature are indicated with asterisk, that is star, like this star. So this star indicates antibonding molecular orbitals, and the molecular orbitals without star are of bonding nature. So when we are observing the calculated progress or calculated effect when the two atoms from larger distance are brought closer and closer. So when we reach, means when the two different atoms reach between such distance, then there is formation of a homonuclear diatomic molecule, in which the molecular orbitals of this type are formed. But when the two atoms are again further brought closer and closer, then they will come at the zero internuclear distance, which is shown here. So when the two atomic orbitals, say 1 sigma g orbitals, are brought closer so that the interatomic distance is 0, then what happens? The two atoms are added like the molecular, when the two atomic orbitals are added together like the atomic orbitals of a single atom. That is, we call it as a united atom or compound atom, you can say. So you can see the atomic orbital is like this. So if we consider the general example, when we take one coin of 1 rupee and one coin of another 1 rupee. So when two coins of 1 rupee each are brought together or collected. So when we collect two coins of 1 rupee each, we say these are 2 rupees. But there are two coins. But we collectively call it as a 2 rupees. So the total amount of the currency is 2. But if we consider that the two coins are fused with each other and forming a single coin, which is 2 rupees coin. So this is called compound coin of 2 rupees. Similarly, means in such compound coin, there is no separation of the coins, or there is no existence of such coins. So we call it as a single atom, but it is called united atom. Means two atoms are brought together or added together forming a new atom. For example, if we take two hydrogen atoms, say these are the atomic orbitals of two hydrogen atoms. When two hydrogen atoms are added and brought at zero internuclear distance, then the resulting atom, that is united atom, is helium. The resulting atom is helium. So we can also consider it the same way, that is when we add two, say, helium atoms together, then the resulting atom is with atomic number 4, that is beryllium. So, but this is like a mathematical equation, but it is not taking place naturally, or there is no existence of such compound or united atoms. But we are taking this progress as for our consideration or for our considering the effect. So it explains the calculated effect of moving two atoms together from a large interatomic distance. So when these atoms are brought together at zero interatomic distance, they are called united atoms. And their individual atomic orbitals are converted into atomic orbitals, not molecular orbitals. But when the two atoms of, say, any hydrogen atom, when they are brought at such the internuclear distance between these range, they are converted into molecular orbitals of bonding and antibonding nature, like 1 sigma G and 1 sigma U star. But still, if you brought, or if you bring the two atoms further closer and closer, finally when the interatomic distance reaches 0, the molecular orbitals are again converted into atomic orbitals, and these atomic orbitals are called atomic orbitals of that united atom. Okay, so this shows the progressive or calculated effect during or when we bring the two atoms closer and closer. So it also explains, this diagram, correlation diagram also explains how the order of molecular orbitals change from boron to F2. And it also explains, means when during this process of studying calculated effect, we are taken into consideration the non-crossing rule. What is this rule? It states that when the two orbitals of the same symmetry, when the orbitals of the same symmetry interact with each other, then their energies should never cross. Their energies should never cross. So their energies must remain same. There should be no crossover of their energies of different atoms of the same symmetry. So you will find here that when, say, we are considering here, you will find that when the atoms are separated, then the atomic orbitals, so far we are considering only from atoms from B2 to F2, molecules, homo-nuclear diatomic molecules from B2 to F2. So in this case, the available atomic orbitals of, say, B2 are 1s, 2s and 2p. So these are for both atoms. So we are having these atomic orbitals available for formation of a molecular orbitals of homo-nuclear diatomic molecules. So when we use, say, 1s, so there are such single molecular orbitals. So when there is formation of a 1 sigma g, then the 1s orbitals of same sign of wave function are brought closer. When the atomic orbitals of different signs of wave functions are brought closer, there is formation of antibonding molecular orbital. Similarly, the molecular orbitals of pi nature, which are present here in the p subchain. So these are px and py. So these are px. Say this is px, this is py, and these are pz orbitals, which are having sigma symmetry. They are having pi symmetry. So they will produce bonding molecular orbitals of pi nature and the antibonding molecular orbitals of pi nature. So when there is bonding nature, means these molecular orbitals, say px and py, these atomic orbitals of px and py of parallels or same symmetry, we will say, and signs of wave functions are identical. Then they will produce pi bonding molecular orbitals, which are called 1 pi u. And here you will find that the at p orbitals of sigma orientation, when undergo linear combination, they will produce the sigma orbital of bonding nature, that is 3 sigma g. So we have shown here this 3 sigma g. So this 3 sigma g has symmetry, same symmetry with this 3s. So we have connected these p orbitals of sigma symmetry with this 3s having also same symmetry. Then you will find that the 2s orbitals also of sigma symmetry, and they have symmetry similar to the 3p, that is 3p z. So they are linked together because they are having same symmetry. Again, there are the pi orbitals, that is 1 pi g star symmetry. So they are having opposite signs of wave functions. So these are, say, px and py. So they will produce the molecular orbitals of this pi g symmetry. Means after linear combination of 2 atomic orbitals, there are 2 such pi star g symmetry orbitals. That is, the degenerate 2 orbitals are there. Here are also 2 degenerate pi u bonding molecular orbitals. So you will get these bonding molecular orbitals and these antibonding molecular orbitals from the parallel or corresponding identical symmetry. Then here these atomic orbitals are having sigma symmetry, and these are from p subchain. So these are p orbitals, pz orbitals, but here the signs of wave functions are opposite to each other. So they will give the 3 sigma u star molecular orbitals. Now you can observe here the 1 sigma g orbital has the united atom having atomic orbitals like this, and these are the atomic orbitals, means molecular orbitals of this 1 sigma star, that is antibonding nature, having opposite signs of wave functions. So here the pi u molecular orbitals of bonding nature are having the signs of wave functions identical. So they are having the shapes of molecular orbitals or atomic orbitals of these united atom like this. So the atomic orbitals, these are molecular orbitals forming after this LCO. These are called 3 sigma g, and when they are forming this united atom, their shape is like this. Similarly, we are having this 2 sigma u star and 1 sigma g star molecular orbitals. So you will find here the shape, and when such 2 molecular orbitals, I mean atomic orbitals, are forming here molecular orbitals, but when they are united together, they will result in the formation of such single, means there are 2 such degenerate orbitals which are converted into single px and py orbitals of united atom. So in this way you will find that the calculated effect when the separated atoms are brought closer and closer and they are converted into the single compound or united atoms. Now we have marked these 2 dotted lines in order to indicate the order of the molecular orbitals formed here, which are indicated here. The molecular orbitals are also indicated here. So when the interatomic distance is between this range, then there is existence of and stability of the resulting molecular orbitals formed. But when we are considering, say, B2 atom, B2 the homo-nuclear diatomic molecule, you will have the order of molecular orbitals like this: 1 sigma g, then what is this? 1 sigma u star. Then here you will find what is 2 sigma g, and here you will find that 1 pi u, and here it is 3 sigma g. 3 sigma g. So we will have, means when we are coming here, there is 3 sigma g orbitals. So in this case, means in the initial stage, starting from B2, so in case of the atom molecules like B2, C2 and N2, B2, C2 and N2, the order of molecular orbitals is specifically here you will find that the pi u, means 2 degenerate orbitals of pi bonding molecular orbital, that is 1 pi u, are lower energy, and the pz orbital, which gives the 3 sigma g symmetry orbitals, are higher in energy. So we have seen that the pi orbitals are filled first, and then the electrons are filled into this sigma symmetry 3 sigma g orbital, molecular orbitals. So the order of the molecular orbitals is like this. So as we move from B2 to C2, the order is same. C2 and N2 is order also same. But when we go to the next, that is O2, which is to this side, means before this F2, the O2 is before F2. So you will find the order is like this: 1 sigma g, then 1 sigma star u, then here what is 2 sigma g, then here it is 1 first stage. Here you will have is sigma g, here it is sigma g lower energy. So this is about 2s orbitals. So this will result in the formation of this 2 sigma g and sigma g star. But we are considering here at this level, you will find that which is lower, this is pi u, it is higher, and sigma g is lower energy. So the order of molecular orbitals here you will find is 3g sigma is lower energy and the pi orbitals are higher energy. So electrons are filled first in sigma molecular orbitals because it is lower, and then the remaining electrons are going into the pi molecular orbitals of bonding nature. Then again the next molecular orbitals filled are degenerate pi g star molecular orbitals, and again the electron may go into the sigma u star molecular orbitals. So this order of molecular orbitals is explained by this correlation diagram. So correlation diagram explains many things. That is, what happens, what is the calculated effect on moving two atoms together from larger interatomic distance. Similarly, it explains the order of molecular orbitals between B2 and F2. So for this range, that is B2, C2, N2, O2 and F2, for this molecule we are studying this order of molecular orbitals. And this is only for ideal consideration. This is not actually happening in the nature. So with this we will stop our discussion. We will see the next point in the next lecture. Please subscribe to this channel and press bell icon and like button. So thank you very much for watching this channel.